Welcome learners. In today's lecture, we are going to start the second chapter from the main textbook of Engineering Electromagnetics by William Haight and John Buck. This chapter talks about electrostatic fields and the Coulomb's law. So let us see what we are going to learn in this chapter. So basically, this chapter gives us an introduction to the Coulomb's law of electrostatic force, and then it tells us how we can use different formulations to understand the effect of electrostatic field in a field theory context. We are also going to learn different tools which are going to help us evaluate or determine the effect of electric field associated with these static charges and their distribution. So let us begin with the first topic from this chapter, and that is, what is electrostatics? So electrostatics is a branch of physics that deals with the phenomena of properties of stationary or slow moving electric charges. So basically we want to understand the behavior of charges at rest. So electrostatics is basically charges which are constant or which are at rest, which means their velocity is zero. So what is going to be the behavior of that static charge in the form of radiation or absorption of waves when present inside an electric field? The charge, though being static, may also behave a slow movement, and that will be cleared when we discuss the behavior of charges or in the interaction of charges between them by the famous equation given by Coulomb's law. So this Coulomb's law is basically going to help us understand that if we have two charges of different polarity, how they are going to affect each other when the force is applied on these charges in the form of attraction or repulsion. So this is what we mean by slow moving electric charges. But before we begin our analysis, we first need to understand what is a charge. So again, I would like to take you back to your earlier level classes to understand this concept. We are not going to dive into this, rather we are just going to remain on the surface and understand what are charges. So charges are basically something that define the characteristics. So charges define the characteristic of any matter. So if you remember, matter is represented into three or rather four stages or four types. So we have solid, liquid, gaseous forms, and then we have plasma. So if we have these kinds of objects in nature, they are going to have charges in them. And if you want to be more specific, the distribution is as such. So if we have a molecule, or we can say matter is consisting of molecules, then it has atoms, and then atoms have the charge values in these three types. Either it can be a negative charge called an electron, it can be a positive charge called a proton, or it can be a neutral element called neutron. Again, the values associated with these charges like electron and protons are negative 1.6 into 10 raised to power minus 19, and you can see its SI unit is coulombs. It can be a plus 1.6 into 10 raised to power minus 19 coulombs. So these are the energies associated with these atomic levels or atomic charges, and obviously a neutral element is going to be a neutral value. So if we again focus ourselves on an atom, let's say if we take any atomic model or any atomic value, so we know atom consists of a central nucleus that has protons and neutrons, and it is surrounded by orbits or shells that have electrons in them. So we can say that these are the electrons that are in a outer orbit of a nucleus or a shell. let's say we have 4 electrons for this scenario, and you know from the Bohr's principle that we need minimum of 2 power n, or starting with 8 outer elements to have a stable atom. So let us say we have this atom, and we normally say that this is electrically neutral with the following condition, that it is going to be electrically neutral. This atom is going to be electrically neutral when the number of protons, let's say in this case we have assume 4 protons, is equal to the number of electrons. So there are 4 electrons. So we say that it is a neutral atom, and which means that its net charge is 0. So let us say that for any reason one of the electron gets displaced from this atomic model. Let us say we consider this electron, and due to some external forces, or if the electron has gained certain energy from the orbits or shell, it gets displaced and it becomes a free electron. Now this free electron has the possibility to become a part of any other atom, or it can act as a conducting electron. So this free electron is moving. But if you look at the atomic structure, now we know that because of one electron being loosed, a cavity or a hole has been created over here. So this is now positively charged, and the electron is moving freely. So now we say that the atom is not electrically neutral because it still has 4 electrons, 4 protons, but the electrons are reduced by 1, that is 3 electrons. So this means that now the net charge in this condition is going to be +1. And whenever this kind of a phenomena occurs, or this scenario appears, we say that this atomic model is now having unequal charges, or it is unbalanced, and thus technically we say that this is now a charged particle. So this is a very important point. So whenever we read this term charged particle, it means that the total atomic level is not neutral at the moment, because the number of protons are not equal to the number of electrons, and the net charge is not 0. So this is what is meant by the term charged particle. Another thing, if you remember from your previous levels, is that this charge represented by symbol Q, having the SI unit of coulombs, is represented as value of plus minus Ne. So this basically tells us that how many electrons are existing inside a charge, with few other informations that this charge, so this is basically equation representing charge present on any atom. So this is the mathematical representation. Another information we get from this mathematical expression is that these charges are conserved, they are quantized, meaning it can be either positive or a negative charge. And important thing in our course of EMT is that charge is a scalar quantity. So these are the important points associated with the representation of a charge in view of its electric energy, where this Ne represents, N is the value of 1 to N, and E is basically the value of the energy stored in this electron or negative charge. So this is a short revision of what a charge is and what are the important terms associated with it, especially the equation which you have seen over here. And whenever the term charged particle appears, we should immediately see that it is talking about an atom which is not electrically neutral, or its net charge is not 0. So now let us go into the historical aspect and see how the electrostatic charges were discovered, or what were the few physical realizations. So if you look at this AI generated animation, human data suggests that it was in the year 600 BC that a guy named Thales, so his name was Thales, basically discovered this phenomena of electrostatic charges. And what basically happened is that he took a piece of amber, So he took a piece of amber, which is a part of a tree that has become solidified because of the liquids it is generating, and it turns it into a orangish brown colored stone. So this is what amber is. So basically he took this piece of amber and started rubbing it with a piece of cloth, sometimes with the wool or any animal's fur. And to his surprise, he saw that various dust particles in the nature were attracted towards this amber. And since the Greeks were more of the philosophers rather than scientists, they decoded this phenomena to something magical. So this is the first findings recorded in human history in 600 BC, where the electrostatic field, or electrostatic charges to be precise, were discovered, and this was the law of attraction from the positive to the negative charges that were happening. Later on, it was in the 1600 era that one of the British physicists, Dr. Gilbert, presented a set of lists or items which had positive and negative charges on them, and he concluded that the materials such as glass was inbuilt charged positively in nature, and other elements like plastic had negative charges onto them. And this was the first time the electrostatic phenomena was basically completed, when both the quantized charges, which means positive charge and a negative charge on various natural elements, were listed. You might have seen an experiment in your physics classes, that how this force of repulsion and attraction basically works. One such example is such. You can see in this example that a plastic straw with negatively charged is placed on a bottle. We rub a balloon that gets negatively charged, and as soon as we bring it in the close vicinity of the charge, the straw starts to move. So this is the force of repulsion between the balloon that is having negative charges and the straw which is also having negative charges on it. So this is a very basic example to see the law of repulsion between these two electrostatic charges. But however, it was in the year 1700s and early 1800s that a French army scientist known as Charles Augustin de Coulomb performed the first scientific experiment using his apparatus, which we know as torsion balance. So this was the apparatus which he designed to verify that the matter existing in nature has charges, and there is a force existing between these charges. And through his experiment, he verified that the forces of attraction and repulsion exist, and this is how the experiment was performed. So basically, Coulomb took this apparatus and called it a torsion balance. And what was the experimental behavior? That it had a torsion head which was movable, or it could rotate in 360-degree. It was surrounded by a glass tube, and inside there was a strong piece of string attached to it, and at the end of the string there was a needle which had a copper bob connected to it. It was a spherical bob, and then the glass container where the needle and the bob was surrounded with a scale to measure the rotation or the angles of deflection or attraction. And in this experiment, basically what happened is that any movement of this needle basically gave us the specific angle of rotation. So initially a blue sphere connected to a needle was charged, and it was brought outside, and it was positively charged by rubbing it with a piece of glass. Again, we knew that glass had positive charge in them. Then this needle, the blue circle or the blue sphere, was then placed back inside this cylinder, and the force of repulsion was noted, as you can see in the animation, that the copper or small bob deflected, and then the wire started to move indicating that it is the maximum force it is experiencing from this blue sphere, and the specific angle on the scale was noted. So the theta was noted for the first scenario. The second observation Coulomb observed is that if you take the positively charged blue sphere and place it to a neutral green sphere, half of the energy from the blue transferred to the green sphere. And again, when this half power blue sphere was put back into the cylinder, there was a small amount of deflection, which meant that the spheres could share their energy. So this was the Coulomb's experiment that was performed. So let us try to put his observation into mathematical translation and see what is the mathematical expression which we got under the observation or made by Coulombs. So Coulomb said that if we take two charges and those charges are at rest, means they are not moving, so they are static charges. So we have to make sure, so let's say if this is charge 1 and this is charge 2, so the two charges are at rest, so this is like this and this is like this, so V equals to 0, V equals to 0. Now the first thing to note is that whenever the two charges are brought in their vicinity, they exist along the same line. So they exist or they move along the same line if the force is acting upon it. But if the distance between them is increased, then the line becomes some form of a spherical movement. So if the distance between them is increased, the movement becomes some form of a curve. So this is the analysis Coulomb made. So in point 2, charges brought closer will move along the line, or their energy will be along the line, which means the force will be acting on a straight line. But if the distance is increased, the movement becomes a curve. So moving is basically in a curve line at larger distances. This distance is between the two charges. The third thing he observed is that whenever the charges are brought closer together, there exists a force. So there exists a force on the two charges in which one charge applies force to the other one, to the other charge, and no charge applies force on itself. Applies force on itself, which means if I have charge q1 and another charge q2 is brought in its vicinity, so it is going to apply a force onto that charge, but this charge q1 is not going to apply a force on itself. So this is not going to happen. So this is the observation which Coulomb's made. The fourth postulate that he presented is that the force being applied, so the force applied can be an attractive force, which means a positive charge and a negative charge, or it can be a repulsive force, which means charges of same nature or strength are going to repel each other. That can be positive positive or a negative negative. So this is the assumption, these are the analysis rather made by Coulomb upon his experiment. So if we have a charge q1 and then we have another charge, let's say negative q2, and if any of them is brought in close vicinity, so this charge is going to apply force onto this and this charge is going to start moving. So we know that the mathematical representation of these two charges can be represented by the equation of force, which is relying on mass into acceleration, and thus the overall equation presented between these two charges by Coulomb was that the force existing between two charges will be q1 and q2, and the distance between them, which is going to be r square. And if we want to get rid of this proportionality, then it is equal to k q1 q2 by r square, where this r square is coming because of the inverse square law, and this is the distance between these two charges. It is r square because we are considering that our objects were sphere, or the surrounding is what we are going to later see spherical, which means that the area of a sphere is 4 pi r square, and as the radius is increased, the area gets increased. So this means the force is going to be spreader in a wider area because of r square, but its strength will be reduced because force is inversely proportional to this distance, which is in square. So this is the mathematical representation of the Coulomb's law, and we can see from here that the force is basically existing between two charges at a certain distance r square. This proportionality is replaced by a constant k, where k is basically the material's property, and the value of k is 1 divided by 4 pi epsilon naught meter per farad, in the sense that if you solve this value, you get the answer of 9 into 10 raised to power 9 meter per farad, where the value of epsilon naught is the permittivity of free space, and its value is 8.85 into 10 raised to power minus 12 farads per meter. So if you incorporate this value over here, you get the value of k, which is the proportionality constant. So these are the equations and the values provided by Coulomb's law whenever we want to find the force that exists between two charges. Now, since we are talking about Coulomb's law and our course is mostly about charges in free space and how to find the distance of charges among themselves and the origin, we rely on vector algebra. So how can we utilize this tool given by Coulomb's law in the form of vector algebra? And we can also do that. So we consider any coordinate system xyz, let's say the rectangular coordinate system, and we have an origin over here. And now we have one charge q1 placed in this coordinate system or in free space, and we have another charge called test charge q, and we want to see the effect of q1 on q2. So we want to see how much force exists between q1 and q. So we can utilize vector algebra and the Coulomb's equation to find the force between these two charges, which is q1 and q. So q1 is our source charge, where the energy is originating from, and q is our test charge. So we can say this is like the field point or the focus point or the test charge. So according to Coulomb's law, we know that the force that exists between two charges is equal to k q1 q2 divided by the distance between them, which is equal to r square. So this is a scalar quantity. If you want to convert it into vector, we need to introduce the unit vector a of r. So if we introduce the unit vector, thus we get the vector notation, and then vector can be represented as such. So this is the vector representation of Coulomb's law in terms of the charges and the vector algebra. So in vector form, we can write vector f is equal to the product between charge q and q1 upon the 4 pi epsilon naught material property, and r square is the distance or the distance vector between q1 and q. So we know that r1 is basically the position vector showing the distance from origin to q1. R is another position vector that is showing the distance from the origin to the test vector q. So this is the distance vector between q1 and q2, that is r minus r1. So hence in our equation of r square, we replace it by r minus r1, and the red box over here is basically representing the values of the unit vector a of r, that is the vector by its Euclidean norm or the magnitude. So if we divide this, we get the unit vector a of r. Hence we have utilized the tool provided to us by Coulomb's equation in representing two charges in space in vector form. So this is the vector form of the Coulomb's law, and this is the equation we get. So another way of writing this, the effect of q1 on q, can also be that F is equal to the force applied on q by q1 is equal to 1 by 4 pi epsilon naught q1 q2 divided by r square into a of r. So this is the vector representation. Sometimes in the book we can also write the notation of the vector force on which the force is applied as f of q. So this is also acceptable, and this form of representation of the forces subscript is also representable. So this is an acceptable form of representing the forces between two, and this is the vector form representation. Now let us look at an example and see how we can find the forces between two charges existing in space. So let us say we want to find the force exerted by, let's say, a charge B on charge A, and the scenario is such. So we have been given the two-dimension coordinate system. Let's say this is x and this is y and this is the origin, and the points given to us are 2 and 4 on the x-axis and 3 and 5 on the y-axis. So the first charge B is at this point, and the value of charge B is 3 coulombs. The second point, or charge A, is having a value of 2 coulombs, and we want to find how much force is exerted by charge B on charge A. So we basically want to find, so let us complete this graph. So okay, so basically we want to find the force applied by B on A. So this is one form of representing the F vector with its subscripts, or we can also write it as F of A. So both of these subscripts are acceptable. So force on A into B is basically, we know it is going to be K q1 q2 divided by r square into unit vector A of r. We can further simplify it as 1 by 4 pi epsilon naught q1 q2 divided by r square into A of r, A of unit vector r, where this A of r is basically the vector r divided by its Euclidean norm, or the magnitude. So this is basically vector r. So we need to find these two. This is the equation, and these are the unknowns that we need to find. So this portion is the scalar part, and this is the vector representation. So let us look into the graph and see what we can extract from this. So we know that vector B is from the origin, so we can draw a line or a position vector, and let us call this r of 1. So this is the vector over here. Similarly, from the origin we can make another position vector towards vector A, and let us call this r of 2. And we not want to find the effect of B onto A, so this is going to be r BA. So we can say this is r BA, the distance vector between these two, which is going to be r2 minus r1. Okay, so the points of contacts are such. So this is how our points are in the matrix. So let us first find the value of r. So r is basically going to be, or this is basically RBA, the distance vector that we need to find between charges B and A. So this is going to be the difference of r of A minus r of B, the direction vectors. So what is r of A? So r of A is basically 2A of x plus 5A of y. So we have taken the values from these points of intersection. Similarly, what is r of B? So r of B is equal to 4A of x plus 3A of y. So these are the positions of RA and RB, or we can say this is R2 minus R1 if we follow these notations. So let's do this as R2 minus R1. Okay, So now RBA is going to be 2ax minus 4ay. So if ax unit vector is the common value, 2 minus 4, plus if ay is the common unit vector between them, so it is 5 minus 3. So it comes out to be minus 2ax plus 2ay. So this is the distance vector RBA, which is minus 2ax plus 2ay. Then we have figured out the r vector, then we can find its absolute value. So if I take RBA and take its absolute, so absolute means you just take the square of the scalar terms. So 2 square plus 2 square, it comes out to be 4 plus 4, 8, and then under root of 8 is 2.828. So this is the magnitude of this vector r. Thus I can say that now my unit vector a of r, or let's say a of r ba, comes out to be r divided by the magnitude of r, which is minus 2ax plus 2ay divided by 2.828. So this is the unit vector which I have found. And now my if we want, we can simplify this as well. So this is minus 0.707 a of x plus 0.707 a of y. So this is even the simplification of this unit vector. So finally my FAB comes out to be, so if I just go for my answer, so finally the force applied on A from charge B, or F of A, comes out to be, just incorporate the value. So I know this equation is 9 into 10 raised to power 9, so I can directly put it as such, 9 into 10 raised to power 9 meters per farad. I know my charge one is 2, and the other charge that I am getting is this is 3. Okay, so this is positive 3, and then I'm going to divide it by r square. So what was r? So r was 2.28, so I'm going to write it as 2.828 square, and multiplied with the unit vector. So this is the unit vector that I got, so minus 0.707 a of x plus 0.707 a of y. So finally the force comes out to be, so finally 4 comes out to be 4.77 into 10 raised to power 9 a of x minus 4.77 into 10 raised to power 9 a of y newtons. So this is the answer, or this is the force being applied by charge B onto charge A. And you can see it's a extremely high value in newtons. You can see it's in 10 raised to power 9. It's a giga value. So this is a huge value, but this is the force being applied between these two charges. I'll leave you with this example, have a practice at this one, and to further understand the concept of force applied between these two charges. Again, here we have charge q1 at point 1, 2 and 3, and then we have charge q2 at point 205, and we need to find force exerted by charge 2 onto q1. So we need to find the force exerted on 2 by 1, or we need to find f of 2. So again we are going to use k q1 q2 divided by r square into ar as a unit vector. This is the vector form representation of Coulomb's law. I'll leave you with the answer, and you can solve this and get back to me in the comments if you are not getting this answer. So the answer f2 comes out to be minus 10a of x plus 20a of y and minus 20a of z newton. So this is the answer, or the force being applied on force 2. Another thing before we conclude this lecture is that, remember, whatever is the force being applied on force 2, the same is applied on the first charge as well. So this means that the Coulomb's law has a magnitude as mutual relation. So mutual relation in the sense that the scalar values or the strength of the charges remain the same, which means that if charge 2 is experiencing a force of minus 10 ax plus 20 ay minus 20 az Newton, the same force is being applied on charge 1, which is q1. The only difference is that its direction will be in the opposite side. So the magnitude remains the same on both the charges in the form of forces. The only difference is that the sign will be opposite, which means that in this case F1 will be equal to 10 ax minus 20 ay plus 20 a of z Newton. So this is an important aspect of the Coulomb's law, and this term is known as that the magnitudes are equally, or they have a mutual force among them, but the direction is always opposite. So this concludes today's lecture. You may provide or verify that the answers you are getting in the comment section. If there is some problem, then I can have a revisit of this solution for better understanding.